Okay, here's a crazy question. Let's say we want to predict the high temperature for April 15th, 2023. It's basically next year. There's no weather forecast that's going to give us that information. Weather forecasts are not reliable a year out. But one thing we could do is we could look at historical data and try to make a statistical prediction. So what I've done is I've downloaded the daily high temperature data for the last 140 or so years from NOAA, and I present here both the time series of the high temperature and the histogram of the high temperature since 1889. You can see there's a lot of variability, and it doesn't look like a very regular signal. It goes up and it goes down, but we can make statistical predictions. For example, we can see it's very unlikely this high temperature is 0. It's also very unlikely it's 100, right? It's got a somewhat narrow band. So that tells us information about what we can expect next year. Okay, so from this data, let's try to pull out an observable. Here what I'm going to do is I'm going to write down the random variable x to denote the high temperature on April 15th, and let's think of y as the random variable that represents the high temperature on the 16th. Just looking at the data, let's cut it off at 60 degrees. That's a nice round number that sits in the middle of the data, and we can see empirically that on April 15th, the probability that the temperature is 60 or larger is 56.7%. On April 16th, the probability that the temperature is 60 or larger is 60%. Of course, it makes sense that it's a little bit more likely to be warm the next day because we're getting closer to summer. But the question, in say any given year, is there a relationship between the temperature on these two subsequent days? Now, if x and y were independent, the probability that x is greater than 60 and y is greater than 60 is the product of these two probabilities, which would give us 0.342. But according to the data, this pairing has happened 57 out of 134 times, so the probability is approximately 0.425. What this tells us is that the temperature on April 15th and the temperature on April 16th are positively correlated. Another way of looking at this is to compute the conditional probability that it's warm on the 16th, given that it's warm on the 15th, and we see that that conditional probability is 75%. Okay, if x and y are two random variables, we've already proved that if x and y are independent, then the expectation of their product is the product of their expectations. Let's define the covariance of x and y to be the expression the expectation of xy minus the expectation of x times the expectation of y. If x and y are independent, this covariance is automatically 0. Let's consider a more general case. Let's say we perform two experiments. Each has a probability 1/2 of success, but they may be correlated and not independent. So for example, x and y can both be 0 or 1. We can see that there's basically 4 probabilities that we could have. The probability that x equals 1 and y equals 1 equals A, probably x equals 1 and y equals 0 is B, and so forth and so on. Using standard addition rules from probability, we see that there's some constraints on A, B, C, and D, and with a little bit of work, we can see that it must be true that A equals D and B equals C. So let's call A and D alpha. That's the probability the two random variables agree, and we'll call the other variable 1/2 minus alpha. That's the probability they don't agree. One extreme of this is if we choose alpha equal to 1/2, meaning that the probability that the random variables are both equal to 1 is 1/2, the probability that they're both equal to 0 is 1/2, and the probability that they differ is 0. In this case, we can compute the covariance. Notice that xy is 1 if and only if x equals 1 and y equals 1, so the expected value of xy is 1/2, and therefore the covariance of x and y is 1/4. Note that it is positive. The other extreme is if we let the probability that x and y be equal to be 0, and the probability that they differ to be 1/2 in each case. In this case, xy is always 0, because x and y can't both be 1, therefore the expected value of xy is 0, and therefore the covariance is -1/4. Note here that it's negative. If we now consider the general case for any alpha, notice that in this case, xy equals 1 with probability alpha, therefore the expected value of xy is alpha, and the covariance is alpha -1/4. Notice in this case that we get a 0 covariance when alpha equals 1/4, but that's exactly the condition for independence. Okay, back to the weather data. For some terminology, let's say that a day is warm if the high temp is 60 or above, and it's cool if the temp is less than 60. We showed from the data before the probability that the next day is warm, given that the current day is warm, is 75% from the data using those two dates. We can also go back to the data and do a similar calculation and find that the probability that the next day is cool, given that today is cool, is 58.6%. So we can model this by like a two-state machine. Think of two states as warm and cool. When we're warm, we return to warm with 75%. When we're cool, we return to cool with 0.586 probability. And from that, we can get the probability of switching from one state to the other. This is an example of something that's called a Markov chain, which we won't get in too much into this lecture, but Markov chains are sort of the canonical way one represents sequences of dependent variables. So Markov chain models allow us to cook up dependency into our variables and see what happens. I'll stop there.